So for today's the lecture is classical statistics. Myself, MD Shahzad Khan, and uh, in particular the lecture will be on ensembles that we shall see in the next slide. Hope you will find this lecture important. So actually the prerequisite here is elementary concept of the statistical mechanics. We have seen in the previous lecture what is the role of the statistical mechanics, how it's connect different domain, microscopic and macroscopic. So whatever in macroscopic domain one is observing, actually it is being contributed by microscopic world. So the basic theme of statistical mechanics is that it's connect the macroscopic world with macroscopic world. Whatever the macroscopic world is happening, especially for thermodynamic variables, it would be advocated by microscopic dynamics or macroscopic mechanics. At first, we are going to see ensembles. Basically, ensembles actually it's a very important term for statistical mechanics point of view. If one is knowing ensembles, then the objective for finding the connectivity between macroscopic and macroscopic domain will become very easy. So ensemble basically it's a mental copies of microstate corresponding to same macrostate. It means a macrostate could have been supported by various type of microstates, and all of these microstates are equiprobable. For example, if there is some energy, there is some given energy, constant energy, and this energy is to be distributed among different person. So the distribution could vary, but the energy is constant and the constraint is given there. We are giving the constraint, but okay, but the distribution of energy among other from person to person, it could vary. Or one can say that if we have some money, let us suppose 100 rupees, and have to distribute among the 5 people, so the distribution could be different. It can be changed from one time to another time. Okay, with respect to time, they are interchanging money among themselves. Within the community, the 100 rupees will be there, but the distribution is changing. So this is all the different distribution corresponding to same constraint. That is, if I am talking about in terms of money, then this different distribution one could say is macrostates. So basically ensembles can be seen in this term, that if there is some macrostate, some constraint, for that constraint there could be different macrostates, and these macrostates, the collection of this microstate for the same macrostate is known as ensembles. It's play a very important role. And the thermodynamic ensemble is a specific variety of statistical ensemble that, among other properties, is in statistical equilibrium and is used to drive the properties of thermodynamic system from the law of classical or quantum mechanics. So the basic idea of this ensemble statistics is that time average is equal to ensemble average. One could say it's a ergodic hypothesis as well. It means if something is happening with respect to time, it's in a time space. If something is happening, one could just take a snapshot of those different happenings or those different movements and just put it at a given cross section, given time. One could put it all together, all these different pictures, and it will give you it is the same way that if one go through the time span, or whether it's at the different instant of time, the picture that he got and is collecting it at a given time, given instant, and then finding the average. So this is the same process. Either you go with respect to time, or you just took its ensemble average. So that is the basic, that is the basic flavor of ensemble statistics. It's a basic properties, a basic concept on which ensemble statistics works, and this is also known as I formally says, ergodic hypothesis. So ensembles is in particularly been categorized in 4 different terms. One can see that's macrocanonical ensemble, canonical ensemble, grand canonical ensemble, isothermal, isobaric ensembles. So macrocanonical ensemble, where the system is totally isolated, and even energy fluctuation is not allowed. It's a very hypothetical system, and in real practice it never occurs. In real practice it is impossible, but it's a very hypothetical system. For the beginning, it is good to start from this particular macrocanonical ensemble, because things become easy and student will observe it as it, with time, if constraint will apply, then it will convert to canonical ensemble, then grand canonical ensemble, and isothermal and isobaric ensemble. So macrocanonical ensemble, it's a very hypothetical ensembles, but again in beginning it is very important for student to know it, because once if they are able, if they are capable to deal with ensemble, or if they know this ensembles, or their grips on this ensembles become strong, then they will able to uh, fluctuate, they will able to switch to canonical ensemble, grand canonical ensemble, and isothermal and isobaric ensembles. So the second ensemble is canonical ensemble. It is a special case of microcanonical ensemble, but at this time the system is not isolated. It means the system is being surrounded by some environment. Sometimes we say it thermal bath, sometimes we say it's universe. So these are all, a system will be in contact with some surroundings, some thermal baths, and where the fluctuation of energy in the system will be allowed. The fluctuation of energy is allowed, not the fluctuation of particles. The system is still closed. Because the system is closed, so no particles can go from inside the system to the outside world. So this is all. But energy fluctuation can take place. This is because to maintain the temperature of with respect to surrounding, the energy fluctuation is happening. It is allowed, and it's a canonical ensembles. And the other one is grand canonical. The third one is grand canonical ensemble, which in general life we see, especially in chemical reactions, where number of particles can vary. Sometimes the number of reactants is something else. The number of products, the number of atoms in reactant is something, and the number of atoms in the product is something. It's some of the molecules or some of the atoms is eloped or is evaporated due to some, it becomes because they changes in some gases form. So here the number of particles is somewhere changing, and it's a very open system. And so here the constraint will be that your chemical potential, volume, and temperature will be maintained. It means that they will be thoroughly constant. That will be our grand canonical ensemble. And then isothermal and isobaric ensemble, where number of particle, pressure, and temperature will be constant, and the fluctuation will take place for volume and energy only. So statistical ensemble, where total energy of system and number of particles in the system are each fixed to a particular values, because this system is totally isolated. There is no surrounding, so there is no exchange of even energy. Exchange is not possible because surrounding is not available. And I formally said that it's a totally hypothetical system. Each of a member of ensembles are required to have the same total energy and particle number, because different macros, all the macrostate will have same energy and same total number of particles. Of course, to maintain this total energy, to maintain the total number of particles, there will be fluctuation. There will be energy distribution could be changed. Energy distribution among different sub-macroscopic energy domain will change, but okay, it will remain the same. The total energy will remain the same, and the system must remain totally isolated, unable to exchange or particle surrounding, in order to stay in statistical equilibrium. On the other hand, in canonical ensemble, it's a closed system, but there's a surrounding with which our system can exchange energy just to maintain the temperature. Because if a system, if there is something in real world, we are always in contact with surrounding. So what's happened in the surrounding, that influences us in terms of energy as well. If the surrounding is if the climate is very good, you will have good mood. If the climate is bad, you will have low mood. Similarly, if any of the system, it is surrounded by some surrounding, the surrounding will have energy, and this energy will be very, very large compared to the system, because surrounding is very large. And since surrounding is very large, and we know that energy is extensive variables, So of course, for this large system, for this large surrounding, the energy will be very large, and this large energy will influence the system's small energy. In particular, we must realize that the surrounding will influence this small system's energy, but this will do nothing with the energy variation in the surrounding, because although its influence will be there, but it will be very feeble, very small, so one can almost neglect it. So it is all the surrounding that will influence the system, and in terms of energy, if it will be high, very high energy, and similarly its energy will be its energy will get tuned. So there will be a temperature, temperature balance in between the systems and surrounding, and to maintain it, there will be fluctuation in the energy. That's why energy fluctuation for canonical system is allowed. Irrespective of that, number of particles is still constant. There's no change in number of particles because the system is closed, so the particles cannot escape from the system. It cannot go across the system, across the boundary of the system. So this canonical ensemble is appropriate for describing closed system which is in or has been in weak thermal contact with heat bath, or one can say surrounding or environment. In different textbooks, they write different terms. Some write heat bath, some write universe, some write surrounding. So in order to be in statistical equilibrium, the system must remain totally closed and may come in to weak thermal contact with other systems that are described by ensembles with same temperature. The other ensemble is grand canonical ensemble. For this ensemble, chemical potential, volume, and temperature will remain fixed. I would like to say that for chemical potential, and the definition of chemical potential, it can be interpreted in different forms. In physics, in chemistry, it's vary, but it is all that one can say that, like in molecules, for example, or in atoms, the electrons to just extract an electrons, or and the amount of energy that is needed to take out one electron from the system, that is known as in chemistry especially, it is chain energy. So it is that chemical potential there. Similarly, chemical potential of atom will different from a system. If suppose there's graphene, it will consist of carbon atom. So to take out one carbon atom from the graphene sheet, whatever the energy will require, that will be the chemical potential of for that system. So there is a variation in definition of chemical potential according to your system. It could be ionization energy. It could be the energy that is required to take out one atom from a system. So it's all varying, but it's an energy that is required to just take out some particles or some electrons or some molecules from a given system. So for this particular canonical ensemble, what we are seeing that temperature and chemical potential will remain same. It is a constant there, but the other thing, the variation will be in number of particles, because the system is not close to one another. It's an open system, just like a chemical reaction. We are doing the chemical reaction somewhere in the maybe in the opening we are doing some hydrogen oxygen some reaction, and we are getting whatever some of the hydrogen is escaped out. So this is open system. So here chemical potential could vary. Similarly, your energy variation is of course taking place. So this type of ensemble will be grand canonical ensemble. The ensembles remain statistical equilibrium if the system comes into weak contact and other systems that are described by ensemble with same temperature and chemical potentials. The references for this lecture is listed here, and in particular, and these books are very important, especially when Professor Suresh Chandra. Several part of the lecture before delivering it, I have gone through this book, so it is my recommendation to go through this book. Thanks all.